Okay, let's continue with this part 2. We're almost done. So now talking about y-intercept, we only have one y-intercept, which I have highlighted in that blue highlighting area right there. So that's when y equals to 3. So they ask you, where's y-intercept? Well, that's when y equals to 3. So that's that point, right? So end behavior. So that's asking you, where does the graph begin and where is the graph going in this case? So now, usually, right, we separate the coordinate system into 4 quadrants. So we call this quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So they're asking you, where does the graph begin and where does the graph end from the left to the right? So now our graph look kind of like this, right? So that means it's starting at quadrant 2 and it's going to quadrant 1 if we start from left to the right. So that's going to be our answer. And behavior, that means where does the 2n going? It's going from quadrant 2 to quadrant 1. Okay, quadrant 2 to quadrant 1. Domain and range. Domain is asking you for the x values. That means what are the possible x values. Now you look at this graph, every single x values are possible, right? When x equal to negative, positive, 0, every single point has a corresponding picture on it. So if you look at the x value number, there are no x value that you cannot have, right? You can have x equal to 10, 20, 30, 50, 1000, negative. So for the domain, we're going to say, well, x is going to equal to all real number. So x can be anything, right? So that symbol means x can be anything. So that symbol right here, like that, is a shortcut for all real number. Okay, all real number. That means every single number that you can think of. So instead of writing down the whole thing, say all real number, we just use that symbol. And that y looking thing, that means exists, right? In, or it means is. So x is all real number. You can think of it like that. So some mathematical symbols. For range. Now for range, that means y values, right? Well, our y value can be a lot of positive numbers. So as you can see, highlighting in yellow right now, we have values for all these different y values that we can have because the graph keeps going up. But the smallest y value we could have, well, some of you might say, oh, it's 0. No, it cannot actually touch 0. So that means all we could say is no matter what x value we can put in terms of the domain, which is the y value, the y value on this function can never be actually smaller than 0. So we say y is bigger than 0. Okay, so y is bigger than 0 is going to be our range. Okay, so that deals with this. So now let's look at something different. So in this situation, we have a y equal to 1/2 to the power of x. So instead of 2 to the power of x, comparing to the last one, 2 to the power of x, comparing to this one, 1/2 to the power of x. So what happens when your base is actually a fraction or less than 1? So when your base is a whole number bigger than 1, like 2, 3, 16, whatever you want it to be, or 2.5, your function gets bigger and bigger really fast. Well, what happens when your function has a base value that is less than 1, which is in this case 1/2? Do you still go up really, really fast? Okay, now let's look at it. Okay, so let's look at this 1/2 situation. Okay, so now let's plot a few points again. So this is going to be, again, we're going to do the x equal to -1. So x equal to -1. So when x equal to -1, we are going to have 1/2 to the power of -1. Now remember, the negative exponent gives you a reciprocal, which in this case is going to flip the fraction backward, and it's going to be 2 to the power 1, which is 2. So now we actually have a point, and the point is -1 and 2. Okay, interesting. It's slightly different from what we have before. So -1 and 2. And now let's try a 0. Well, okay, so 1/2 to the power of 0. Now anything to the power of 0 is 1. So, okay, cool. 0, 1. Next point, x equal to 1. So 1/2 to the power of 1. 1/2 to the power of 1 is 1/2. So, okay, so 1 and 1/2. And next point, let's try 2. So 1/2 to the power of 2. Now, what is 1/2 to the power of 2? That will actually be 1/4 because the 2 gets squared, right? So that's 1 and 1/4. Wait a second, these numbers are not getting bigger. Look, 2, 1, 1/2, 1/4. These are actually getting smaller or closer to 0 when you think about it. So let's say you try another one, 3. So what happened at 3? Well, 3, you get 1/2 to the power of 3, which is 1/8. So that's even smaller. So that's 1 and 1/8. So these numbers are even smaller. So 1/2 is 0.5, right? 1/4 is 0.25. 1/8 is point something like 125 or something. So that's even smaller. So these numbers are not getting bigger. So let's plot them. So -1, we get a 2. Okay, so -1 and 2. 0, we get a 1 right there. 1, we get a 0.5 right here. Right, 1, we get a 0.5. And the next point, oops, sorry, that's 2 and that's 3. So 2, we get a 1/4. Oh, okay, it's really hard to draw now. 3, we get a 1/8. Okay, so that's getting really, really small. Now, if we try another number, so for example, now you can see the trend, right? But let's say you try -2, you actually discover that -2 goes to 4 and -3. So these one I'm not working out. I'm just telling you that -2 goes to 4, -3 goes to 8, and so on. So if you line them up, now you don't have a increasing function, you actually have a decreasing function. A function that is decreasing instead of increasing. But it's still not actually going to 0 though. So it still have the same problem that the other type of function have, which is it's getting closer and closer to 0 and closer to 0, but it's never actually crossing it. So it still has that horizontal asymptote. So these are different compared to what we had before. So let's go back up. What we have before, the hyperfunction that's going up, is called exponential growth. So it's growing, right? And what we have now, when the base is less than 0, so when the base is less than 1, so when the base is 1/2 right here. So what we have in this case is we actually have something called exponential decay. So exponential decay. So that means it's getting smaller, right? Exponential decay. Okay, so it all depends on the base, not on the x, right? On the base in front of the x. So if the base is between 0 and 1, so that means when we have a function where that base right here is between 0 and 1, for example, let's say like 0.3, which is between 0 and 1, right? And then to the power of x, so that's the function. Then we're going to get an exponential decay function. Decay. And if that x is greater than 1, if that b is greater than 1, which is anything you want. No, it could be like 7.4, which is bigger than 1, right? To the power of x. So if the function is like that, right? So the important thing is this base value. So if the base is bigger than 1, then you have yourself an exponential growth, right? So it's getting bigger. Okay, so that's it for this unit 1's, section 1's note. And I'll post the homework on the description. You can actually see the homework in here, assignment page 439. So I'll post everything that you need on the description. Okay, bye.